Welcome to another GC Basic demonstration. This is for the PIC18FxQ24 series. This is part 13. Well, in this part 13, we're going to look at using SPI. In this example, we're going to use a graphical LCD, but it represents the use of SPI with GC Basic. Been a few delays in getting this video out. That's because I've been working on another support issue with respect to floats, but all sorted. So don't forget to like and subscribe, thumbs up, etc., and let it run all the way through. Great, so this is 13 SPI, unlucky for some. SPI, serial peripheral interface, and I'm only using GLCD as an example, and I might actually dig out another GLCD for you whilst I'm doing this. Okay, so what I'm expecting you to have in terms of prerequisites is obviously the software, programmer, Q24, and you've tested that, LEDs, pots, switches, USB, TTL, and this GLCD device. Now, let me show you what's on the desk, okay? Desk cam. Here it is. It's actually operating at the moment. It's down here, this little thing down here. For the eagle-eyed view, I've changed the board. I have 10 of these, so why have I changed it? Because this doesn't have the LEDs all connected. It has, I mean, it makes no difference, but just the eagle-eyed will have noticed this is a slightly different board, a set of transistors here for level conversion, etc. It's the same board essentially, but we'll go into that very shortly anyway, the configuration. So what also is important before I go any further is the power domain. I'm connecting up the power domain. Let me just put up where I'm putting my 5 volts so that we all agree. I've applied 5 volts to heat, even though I'm not using serial in this demonstration. If you wanted to debug this with serial, you must apply the VDD on that power domain. And if I go back to my camera, you can make it out just here on this white cable here. There's a 5 volt supply into C.7. What was C.7 is actually now the VDDIO2 power domain. Right, with that settled, let's get into what SPI is. Serial peripheral interface. It's an interface bus that's used between the microcontroller and computers, to be quite frank, and other devices. I said small peripherals, such as GLCD, shift registers, SDI cards. SD cards are the same, but it is a very common interface, and it uses a separate clock to data line. You can remember from the previous I2C, we use a share. We do a lot of sharing on that line. This one here uses separate clocks and data lines along with a select line to choose which device you want to control. So you'll have multiple connections. You'll have a clock line, you'll have a data in and out line potentially, you'll have a chip select line, you might have a reset line, and you might have other lines. And we've got all of those in this because it sort of demonstrates the complexity of what you might have to do. But you can connect. The majority of those are shared. You'd have a common clock, common data out, common data in, command lines, etc. But the chip select is the only thing that you might actually have different to each particular SPI device, because you can have many of them. Now, in my particular case, in this particular one, I've actually selected and developed this little diagram, and why I've changed it, the layout slightly and put it in bold. These are the ones I've got connected up. VDIO2 transmit is connected. We're not going to use that. And then the 5 lines that we're going to be using, which is the serial data out, serial clock. This particular GLCD needs a reset. I need a chip select now. You could ignore chip select if you only had one device, but because I'm assuming you're going to have more than one, we're using chip select. And then we have a DC, and that means data or command line. And depending what the protocol is doing, it's going to toggle that data and command line. And it will then inform the target device what to do. I'm sending a command, you'd actually raise the signal, and for data, you lower the signal. And so all that's part of the protocol that's supported within the SPI communications itself. So What I've got is this little GLCD, and it's got these lines connected. As you can see, I have not shown the ground and VDD, which I've got as 5 volts. I've got a yellow clock line, a blue data line, reset, data or command, and CS, and I've got all those connected. I might even be using the same colors. I don't remember if I did that, but I certainly always use blue for my data. I always use yellow for my clock. So I'm very clear about what I'm doing. That way I don't get confused, and it's clearly working, so it tells me something. More on the setup. So once you've decided that you're going to use an SPI, you need to do some definitions, and I'm going to show you these inside the actual a program very shortly. But if you're using a PPS chip, you need to set up the PPS, and it needs to match the parameters. And these parameters, as I've spoken about before, is the data out and clock, DC, CS, and reset lines. And those lines need to be defined as constants, and I'll explain why they're constants very shortly. And that specification comes from the driver, not GC Basic. It's whoever implemented the driver for this particular type of device, and they're documented in the help. So we need 5 constants: data out and the clock, DC, CS, and reset as shown. Now, what's important is as I've said, the PPS needs to match that. And the things that are controlled by PPS are the data out, potentially data in if you're using it, and the clock line. They are, if you're going to use the hardware, you need to set the PPS. Be very clear. But we're going to show a little trick in most of the SPI implementations. There's a little trick so we can use software as well. Okay. Now, unlike I²C, there is no way of determining if something is going to work. With I²C, we could use I²C discovery. Well, with SPI, things might not work straight away. So when things don't work straight away, check the connections. Check them, not once, but twice, but 3 times. Are you getting a signal? You might even have to write your own little program to toggle the line and then put a meter on it or something. You need to check your connections, because there are things we do know. We know that the GLCD driver works. We have lots of demonstrations and we know it works. So don't be looking and going, oh, it's that, because it's probably not that. It's not likely to be the libraries, because you have to work through the checklist first. So go back and check your connections. Write a program that pulses a signal on each of the lines. So that's clock, data, reset, CS, and DC lines. Put a clock on it and make sure that it's actually got a signal on it. Then always use Software SPI first. And we'll show you that to prove the connectivity. Before, if you jump straight to a hardware solution, you're just introducing a level of complexity that's not necessary. Your target architecture might be to use the hardware SPI with PPS when appropriate, but always make sure that you've got software working first. It's just a general rule, okay? Great. Now, I'm just going to show you something first. So I'm actually going to go across the lab and grab something, okay? I'll be back. I'm back. I'm just going to show you another SPI GLCD. And it works. It works exactly the same principle. So what we're going to see is not this. Look, slightly larger. You can see a picture of me in there, and the camera. That's a 7-inch display. That's also SPI. Okay. Oh, there you go. I've caught something in here. But essentially, there we go. Just reset that. So that is a 7-inch SPI display. Works fine. Works exactly the same principle. And it works great. It's just as fast, by the way. Okay, you can see it resetting. I'm sorry about the little fuzzy display on the GLCD itself. That's nothing I can do about it. That's the actual lighting in the lab here. So let's go back to what we're going to go through. So we're going to look at the operations. We've seen it working. We'll look at software SPI called bit banging, and then we'll look at hardware with PPS, of course. But we're also going to introduce conditional compilation, and that's important because it will allow you to switch between software and hardware quite nicely. So if we just go back into here, which is the demonstration I'm working on, and I've opened up demonstration 230. 230, I shall zoom in because I've been obviously clearly working here. Control B, Control J gets rid of all the little windows. Look, we have a program. It's called SPI and GLCD using an SSD 1331. There are quite a number that support SPI. I'm just using this one. Great. What have we got in here? We've got the standard header, blah, blah, blah. We've got a PPS in here. I'll come into the PPS shortly. And then the rest of this is the same. I have updated the IO line to show that we're using SPI. Simple as that. Okay. The rest of this is the same. And then we come into the setup for the GLCD, and it's here. So same as the previous demonstration, we saw how to set up an include line. We say include the GLCD driver, and then we just tell it which one we want. And it's this here. Just make sure you can see that. It's like, there's a gap. So it says GLCD type, and then it's the type you want. And there's many different types. I think there's 35 or so. And then you need to set up these constants. Well, without going into flicking back up the screen here, they are connected to C4, 3, 2, 1, and 0, respectively, for data out, clock, reset, CS line, and the data and command line. And if I show you the desk cam, you can see that in the back of here, there's a row of pins connected in here, and they're connected through to these lines on here. So all these are coming across and just connecting into here to the correct connections. Now, in the majority of the SPI implementations, you will find the following line. It will say something like this: hash define the device underscore hardware SPI. And if you comment that out, it will just use bit banging. I am not going to show you the rest of the program because, to be quite honest, it's quite boring. You've seen all this before. This is all about setting the contrast and putting stuff on the screen, etc. Let's program that because we've got it commented out. So that I've commented out using the hardware SPI. Now, because I've done that, magic will happen, hopefully. And here we have. I can zoom in on that a bit more. It's just programming it. You saw that was steady in black and white. That's just a refresh on it. Look, it's putting things on the screen. That's what's important. It's just flashing through, and it's doing exactly what we saw in the previous demonstration. So this is actually showing you strings, characters, numbers, circles, lines, fills, and it's all in color. And it's the same on that big screen I showed you. It's just that it's unwieldy to use. So you can see down here in these little numbers here, they're all sort of rattling away. That's all coming from the program. And it's using software SPI. How do I know that? It's because, as I said up here, is that the program itself supports this type of command. It says, if that exists, use hardware. If it does not exist, then do something different. So why don't we look at that in particular? Because that's an interesting concept, and that's called conditional compilation. And we're already using that conditional compilation inside of the PPS. Inside of here, in the sub called PPS, there is already some compilation. So I've used PPS tool to give me my setup, and it gave me, let me just change the zoom here, get into there. I've used PPS tool to give me my setup, and this is what it gave me. It gave me this setup here. I'll show you that. I came into PPS tool and generated the standard things. So I wanted SDO, which is serial data out, and serial clock out. And then it gave me these 3 entries in here. I pasted it in, and then what I did, I said the following: conditional compilation. I said if defined, with a hash in front of it. So this will change the generated code. It will do one thing if it's defined. Hash means else, do something different. And it will only put one set of code in. So it's not an if statement within the assembler. This is the compiler will do one thing or the other and only that. And so if this is defined, it will set up the PPS for us. Else, it will clear the PPS. Why is that important? Because if you're switching between the two and you don't clear those variables, PPS is still active. You have to power cycle it. So this is a way of showing you that says, oh, well, this is quite clever. And you can use this to change the configuration. If def, and there's many different conditional controls. So what does it do? If we look inside of the source program for this library, that's dangerous. And we'll look at this one here. It's called send a command, and it sends lots of commands. You can see this is actually in the library. This is for setting the contrast. We're going to look at how it's different using conditional compilation. Control F. I'm just going to find something, and I'm going to find that actual command inside of this library. If only I could find it, wouldn't that be great? There's 78 instances of send command. Well, obviously there's lots of commands. Look, there's lots of them. I thought if I put a caret in front of it, it would. Oh, that's not what I'm looking for. I'm looking for this. Where is send command? I'll find it in a minute. We'll just cursor through, shall we? And just let it run. This is all the commands that it's sending out. What I'm looking for is the actual command itself. Oh, here it is. Here it is. Send command. So it says in here, look, supporting what was at the top of the program. If this constant exists, do something. If not, do something different. So where was I? Because I've just had the vehicle breakdown. People come to my home to sort out my EV car. Anyway, so two constants. One constant, SSD 1331 hardware, do one thing. If not defined, do something different. So what's it going to do in each case? Let's look at this one. If we open it up, it says repeat 8 times. And basically what it's doing, it's sending out bit by bit a variable called send byte. And if the 7th bit is on, toggle the data out on or off depending on its own state. So all it's going to do is set a bit on the bit on or off, and that's an output line. It's an actual port, so it will toggle it up and down, and then whilst it's in that state, it does a clock. It clocks it out, and then it rotates that byte to the left, which basically means what was the 6th byte becomes the 7th, and it does it 8 times. It's actually called bit banging. There are some control signals in there. As you can see, there's a set the chip select line to on. If you look in here, it set it to off initially. So that says I'm talking to you. It's a data command, so therefore it set it to off. And these are IO lines, so they're going on and off externally. And this is bit banging. But what would happen if it was hardware? Well, let's have a look inside there. It essentially says send out a single byte, the same byte, send it using a function. It's a routine, we'll call it a routine, called fast hardware SPI transfer. And all it does, it just pokes it out on the bus. and it uses the hardware. So you've got these two options, and if one works, the software works, then at least you know you've got all your ports set up, your connectivity is set up, and you've got it documented. Then turn on the hardware SPI. So in my example here, all I'm going to do to turn it on is uncomment this particular line here. The moment I uncomment that, Control V, all of a sudden the PPS will be used, and will the hardware SPI functions be used. I have now just pushed compile. I'll go into this mode so we can see it all happening. And you'll see very little difference actually on the display. It might be slightly faster, but you get different functionalities with the hardware. You can now use interrupts with ease, and you can do various different other controls using the hardware option. And it's running through the demonstration. It is faster. It's actually noticeably faster refreshing that screen. On the bigger 7-inch screen I show you, it's just as fast, by the way. It uses some of the internal capabilities of that particular display to be extremely fast. It's just as rapid as this, if not faster. So it's running at 64 megahertz. Hardware SPI is operational. How do I know that? If we look inside the assembly, it's going to be hard for me to convince you it's doing anything, but I'm going to do a search for the same command, and here it is. And it says in here, this is the same routine we were looking at a moment ago, and it says set the chip select off, and then use a function called SPI, and it's fast hardware SPI transfer, and here's the byte getting moved out. Now you don't need to see all that normally, but that just proves to you that these things are all happening at the same, depending on how the compilation is actually configured. It's the same for memory devices, same for SD cards, large SD devices, etc., etc. It's extremely simple to use. So the commands are down to, the actual hardware commands are things like hardware SPI transfer, fast hardware SPI transfer. Those are the basic commands. So if I come into here and I press function key F1, it will take me into the help. And there is the help for fast SPI transfer. I will zoom in, and if I look in the help itself, command reference, serial communication, or SPI, sorry, and here it is, SPI overview. There's an overview of how it all operates and the commands that are required. And as I've shown you, a lot of that for all the library devices are masked from you. You don't need to be concerned, but the raw commands are very simple. You use SPI transfer to transfer a bit in, a byte in and a byte out, or you use fast SPI transfer just to send one byte out. Very, very simple. Let me check what else I wanted to show you. That was it. We'll call that a day for now. So next is pulse width modulation, 6 ways to dim those LEDs. I'll go back to the other board and put this one back in its drawer. And then we'll go through the last few videos. So PMW, 6 ways. Could be 7 ways, because it used to say 7 ways, but then I realized it might be 6. We'll find out what goes on. Enjoy.